All right, so for our next section of notes, we're actually going to kind of be getting into the first steps for analyzing circuits. And in order to do that, we have to talk about one of the most easily recognizable and important rules with circuit analysis, and that is going to be Ohm's law. We've already seen this a little bit, but we're going to dive into that a little bit more in this section. So Ohm's law describes the relationship between that potential difference, or the voltage, or the EMF as we called it, across a conductor with the current passing through it. And a conductor is something that allows electrons to flow, but as that electrons are flowing through it, it is going to have some type of resistance. And we talked about in the last section, resistance is resistivity times a cross-sectional area divided by the length of the wire. So Ohm's law is what we use to help us determine what that current is going to be going through that conductor. Now, an important thing to know, Ohm's law is not a law of nature. What does that mean? It means that materials that apply to Ohm's law that follow this formula are considered ohmic. There are non-ohmic materials out there too, meaning that if I increase the voltage, the current might not increase linearly with that voltage. So there are a lot of things that are not ohmic, and what we're going to focus on, though, in this class is going to be ohmic resistors. So Ohm's law means that if I have a graph of current versus voltage, or I could switch it and I could do voltage versus current, I should get a nice linear line, meaning that the current that is directly proportional to the voltage being applied across that resistor. So it's other materials that are non-ohmic, which I kind of talked about, meaning that it just means that this is not going to be the shape of the line. It's not directly proportionally. We could have batteries. Batteries a lot of time have internal resistance. Capacitors change based on how they're charged. That's something we'll take a look at in physics too. But what this means is if I have a battery, there's my battery, positive side, negative side, and let's say I have a light bulb that's attached to it. This is the symbol for a light bulb. We'll talk about that more later. So that's my light bulb. If this is 1.5 volts, I'm going to get some current going through that light bulb. If I double this and I say, let's make this 3 volts, well, the light bulb is going to shine brighter, and the reason it shines brighter is because it's going to have twice the current going through it that it initially did. So that's what Ohm's law is saying. The more voltage I apply across a resistor, the more current that's going to go through it. So resistors are something that we'll take a look at a little bit, especially in our lab. That's going to be right following the next section when we take a look at the relationship between voltage and current. But resistors are circuit elements that are designed to have certain resistances. And they do that for a lot of different reasons. But mainly they help control the current that's going through the electrical components. So these resistors are very common resistors in computers and stuff like that. And that is so that they have specific paths for current, and they dissipate some of that voltage and they turn it into heat. Now, there's a lot of different types of resistors. If you look inside of a toaster is essentially, I should pick a different color here. A toaster is essentially a ton of resistors, except instead of the resistors like we saw in the last slide that looked like they were out of computers, these are just resistors that have wires that with high resistivity. So then those wires then heat up, and as they heat up, they start to glow, and that is, of course, in this case, used for cooking or toasting your bread. There are a lot of other types of examples of that, though, too, right? You have a defroster in your car, the rear defroster of your car. That's just wires back and forth across your car that heat up to help warm up the glass and get rid of your condensation that's inside the car. But toaster, if you have an electric stove, that's just a huge resistor that just heats up. These are the circuit elements that we've kind of talked about already, and those are inside of a lot of different electronic devices. And you'll see that they all have different or some of them might have the same, but there are different colors. And this is the color code that's used for resistors. And we do a color code lab that we learn quickly about what these numbers represent. Back when I was in high school, in my physics class, I had to memorize the color code chart. That is not something at all you will be needing to do. But we also have different practical purposes like light-sensitive resistors. So here's what happens. The light, ambient light, shines on this resistor. And when it's sunny out, this resistor is full and it stops the flow of electrons. And then when the sun goes away, it's open, and then this light can go on because the current is flowing through it. So it detects the change in the light and turns this light on and off throughout the day. So it's a photoelectric or a photosensitive resistor, which is kind of cool. But when we're looking at our basic light bulb that we're going to be using to analyze circuits, there's a couple different things going inside of it. It's a light bulb really is just a resistor. It resists the flow of electrons. Now here's what happens. The electrons, they're attached at the bottom. They go up this wire and they go around this filament. Now in regular light bulbs, that is a tungsten filament, and that tungsten heats up and it starts to glow, and then there's other gas inside of that light bulb, and that's what allows it to flow. But those electrons have to keep flowing, and then they flow out the side and they continue through the circuit. So if you ever look at a light bulb, there's a connector on the bottom, but then you have to screw it in, and that connector on the side is what completes the circuit for that path. So that's our basic light bulb concept and how electrons flow through the light bulb. And part of lab 7.4 was analyzing exactly how an electric light bulb flows, and this actually confirms that right here. So when we look at this easiest simple circuit that we can have, our light bulbs that we use have roughly 3 ohms. But if I hook one side up to the positive side, one side up and the other side up to the negative side, one side being the bottom, one side being the side, and I could put this wire anywhere on the side and anywhere on the bottom, I create a circuit. So when we look at that circuit, we're going to be analyzing the resistance within this light bulb. Now, we did a whole section about understanding like the resistivity within a wire, and we know that this wire does have some type of resistance, but we in physics, when we're analyzing this, we call these an ideal wire, and we're going to say that wire resistance, the internal resistance, is 0 ohms. It's so small that it doesn't matter. That just means that it's allowing electrons to flow without slowing them down. So this makes sense. If I have a 3-volt battery, then where is that voltage drop occurring? Well, it's going to drop across that. All 3 volts is going to drop across the light bulb. So that's how we will start to analyze circuits. So if this resistor here, that's what I'm saying, is that it could be a resistor, it could be a light bulb, but there's 3 volts that are going through this wire. It hits the resistance, or hits the resistor. That voltage, that electric potential, drops down to 0 volts when it leaves the wire, but the current keeps going through it. So that's how we use this ideal wire model to analyze what's going on with this circuit. Current moves through the resistor, and as it goes across the resistor, it drops in electric potential. It drops in voltage when the current passes through it. So here's a little quick check. I have trial 1 has 1 light bulb, trial 2 has 2 light bulbs, and we're wondering which bulbs are brighter. So if these are both 3-volt light bulbs, 3-volt batteries, in trial 1, all 3 volts are going to drop across this light bulb. But we can kind of use our thinking of this and what has to happen in trial 2. Well, the voltage drops across the light bulb. So if this one gets 3 volts and I have a 3-volt battery, that would mean that this guy gets 0 volts. Well, that doesn't make any sense, because then why does it get all the voltage? So it doesn't. It actually, they equally get voltage based on their resistance, and that's how Ohm's law is going to help us. So actually, this one gets 1.5 volts, and this one gets 1.5 volts. each light bulb will get 1.5 volts. So in trial 2, they only get 1.5 volts. In trial 1, it gets 3 volts. So the brightness is less for trial 2. And that's going to be our quick little introduction into Ohm's law. So remember, the big thing with Ohm's law is that the current is equal to the voltage divided by the resistance. Resistance is measured in ohms. That's the resistors that we were talking about. Now, going forward, we're going to start to use this concept, and especially in chapter 23, we only have a little bit left of chapter 22, and it's still just kind of a conceptual introduction. But in chapter 3, we're going to be using this formula to really be able to analyze these types of circuits. So right now, we're just kind of using our common sense to analyze them. But as we go through into chapter 23, we're really going to be able to use math to analyze them. So there's one last concept that we'll talk about. We're going to talk a little bit about energy and power as it pertains to circuits, and we're going to go ahead and do that in the next segment.